in this 6th lecture on the language Verilog, we will be discussing today some additional features of the language, namely you recall earlier we had mentioned that when you have memory as part of a design system, we usually incorporate it as an instantiated module. We take the memory block as a pre-designed one available in the library, we can simply pick it up and put it in our design. So, we will see today an alternate way of representing and using memory. For instance, if we need a very small amount of memory in a design, we do not find a matching memory block in the library. So, in that case what to do? And after that we will be looking at how we write the Verilog test benches, and then what are the different specific things that need to be understood whenever you want to write and use a Verilog test bench along with a designed module. Okay. So, we start with having another look on the modeling of memory systems. Now, as I had mentioned earlier, if you recall, memory is included in a design by instantiating pre-designed module which can be picked up from a library. Okay. Memory is designed or included by instantiating a pre-designed module, but this is possible provided you have such a memory module available in the library and the corresponding size of the memory module matches with your requirement. So, as an alternative, what we can do, the language Verilog also supports this, we can model memory using 2-dimensional arrays. 2-dimensional arrays is essentially an array of register variables. So, you can treat it as a register bank. So, this is, you can regard it as the behavioral model of the memory system. Well, actual memory system is not just an array of registers, it is something more than that. There is some special layout and special way they are fabricated, but this view of the memory is often used for simulation purposes. But when you are talking about fabrication, when your ultimate aim is to design and fabricate the chip, then you would have to instantiate a proper memory block from the library. But if you have small memory requirements in a design, then you can use it even for synthesis, this alternate way, modeling memory as a 2-dimensional array. Now, let us see how we can do this. First, a typical declaration. This is how we can declare a 2-dimensional array, or you can say an array of register variables. Here this declaration says that this is a register type variable and the size of the register type variable is 8 bits and it is an array. So, actually what will be there, this will be treated as an array of 1024 registers with index going from 0 up to 1023. There will be so many register variables, the name of this 2-dimensional array will be given as mem, and each of the words will be of size 8. Okay. So, this is how we can define a 2-dimensional array of storage locations which can be treated as an array of register variables. So, if we access this structure as say mem of say I, this will actually return a register type variable of size 8 which logically means the contents of the ith location of the memory. So, we can model a memory system behaviorally by this, and you can access the ith location using simply mem I. This is what you can do. But I had said that you typically use this kind of a memory modeling when your target is to simulate. That is the most common scenario. So, next we shall see that once we have designed such a memory system, so how we can initialize it. Initialization can go like this. See, this initializing memory, what we are talking here, this is from the point of view of simulation. Typically what happens in case of simulation is that you have a memory system which you have included in your design, and you have say some data that you want to load into the memory system for the purpose of initialization. So, one alternative you have, for of course you can make explicit assignments of the values to the memory locations and make the initialization. Now as an alternative, and this is possible only for simulation, again I am telling you that you can do one thing, you can specify the name of a file on the disk and you can read the values of the memory location from the disk and you can populate or load the memory with those values. So, this is one very common way of initializing memory by reading the data patterns from a specified disk file. This, as I told you, this is used for designs where you just only want to simulate something, not synthesize, or we will see later that when you are using a test bench, means I want to generate the test patterns that I need to apply to a circuit I have already designed for the purpose of testing. There also the test vectors can be available in a disk file. I can read from the disk, I can apply them to the circuit. Okay. So, these are the two different situations where we can read the patterns from a disk file and load the memory with it. Now, in Verilog there are two functions that are available, read mem b and read mem h. B and h basically refers to the radix of the number that are read in. B means binary, h means hex. Well, if it is binary, then your file will be containing a streams of zeros and ones only. If it is h, it will contain hexadecimal characters. Now, the parameters are very similar. Parameter, the first parameter specifies the name of the file from where the data has to be read. The second parameter names the register or the two dimensional array that you have defined in your Verilog program. The last two parameters are optional. Well, if you do not specify that, then the entire memory whatever you have defined, that will be populated by reading the data values. But you have an alternative, you can specify the start address and the stop address of the memory, and you can load only that part of the memory. So, if you have a bigger memory, you can choose to load only certain part of it. The rest possibly you will be using a scratch pad, you need not initialize them. Okay. So, if you have such a requirement, you can specify both the starting and the stopping address of the memory, and the data which are read from disk, they will be loaded in this area. So, read MB and read MH both are similar in terms of its usage. The difference again I am telling you is here we are using the binary data, here you are using hexadecimal data. Oh, okay. So, the question is that if the file size does not matches with the memory size other things, okay, there may be two things. First is that you have a memory defined, say this is your memory, let us say the name is mem. There may be one alternative where the file data, the data which are there in the file are insufficient. Insufficient means whatever data you are asking to read from the file, there are so many data. So, this will give a file system error that you do not have so many data in the file, there will be error will be given. And alternatively, suppose you have the other way around, the file contain more data, or in some one particular line you have possibly missed some digit, but it will not check further, it will read sequentially the digits as they appear. And moreover, suppose you say this is a disk file and you give a command to read say from start address 100 to stop address say 150. Now, in the disk, well, you will be reading from the beginning only, not from offset 100, but you will be reading the first 51 words or numbers, whatever size you have defined them to be, and you will be loading them into this mem array starting from index 100 up to 150. So, actually here again there can be two things. One is that you do not have sufficient data in the file, in that case again that error will be given flagged, and other thing is that the start and stop, whatever boundary you have given here, the mem is not defined for some of those range values. There also the simulator will give an error, that means you are trying to access something out of the bound. So, the simulator, since it is working in an interpreted way, it can give all the error messages wherever it encounters during execution, right. So, a simple example. So, you have defined a memory system 1024 words, 8 bits each, and you can give a command like this: read memh, file name, name of the variable. The third and fourth parameters I am omitting, those are optional. So, the entire memory will be populated by data from the given file. Okay, fine. This is not the instantiation of the module. This I am defining the memory as a 2-dimensional array, as an array of registers. Okay. Now let us now, yeah, yes.
Called memory. Memory is the like instantiation of the specialized memory or just registers?
When you say that I am instantiating a memory from the library, that is not a register array, that is the entire specialized memory designed and fabricated your. So, means at the high level you will be talking about the behavioral specification when you are simulating, but you can use that same module up to the layout level, because it is available up to the layout, that detail is available in the library. As an example, we look at a couple of memory types, how we can model them in Verilog. So, the first example we take is a single port RAM. Single port RAM means there is only one read write access port with synchronous read write. Synchronous read write means all read write are taking place in synchronism with a clock. So, here you can say in this module there is a signal called a clock, there are read write chip select as usual that are there for memory chips, we have the address and the data. Now, in this example description we have defined this address to be of 10 bits, data to be of 8 bits. So, there are 1024 locations of 8 bits each. Clock, read write, CS, these are all input signals. Data can be input or output. So, other than input and output there is another kind of declaration in out. In out means it is a bidirectional signal, and Verilog we can also define a signal as in out. Now, here we are defining memory as a behavioral block reg mem. So, it is a 2-dimensional array. Since the address is of 10 bits, we are defining mem of size 2 to the power 10, right. And the data which will be outputted during read operation, that we are defining it as a reg value d out. Now, you see the way we have given. First one is a continuous assignment statement. Data is assigned a value depending on chip select and read. The data will be assigned a value only if it is a read operation, which means that the chip select is active. We are assuming that all the signals are active high in this example. So, if chip select is true and read is true, then whatever d out has been computed, that will get assigned, or else this is tri-state 8 Z's, or else you force it to the tri-state value, which means you do not assign anything, leave it as it is. Now, you see there are two concurrent always blocks running. both are triggered by the positive edge of the clock. The first one is for memory write, the second one is for memory read. Memory write means, here is the condition, chip select, write is active and read is not active, because by mistake both read and write may be active at the same time. Just for checking that, you check that the read is low. If it is so, then the data whatever is coming from outside, that gets written into mem_addr. That is memory write operation. And for memory read, you again check if it is chip select and read and not write. Then you read the contents of the memory and do not store in data, but rather store in dout. Storage in data will be done asynchronously here. Okay. So, this is one typical example where we have synchronous read write. But if you have asynchronous read write, which is common to, you can say, most of the chips which we use today, there are no clocks available with the memories. There we would not use these statements triggered by POSH clock, but rather, yes.
Instead of this assign, had we not used assign, and we always block, instead of dout we use data.
Instead of dout we have used data here.
Assign statement, sir. We don't
Yes.
use assign statement. Instead of dout in the always block, we use data there.
Data out here,
Yes, sir. And initially we assign data to an 8-bit Z.
and also here also you write data,
So we don't use that time.
but
It is not there.
yeah, it is fine, but there is only one thing, this explicitly is done due to the reason that when you are not doing any read or write anything, I want the data line to be tri-stated.
So that we can do with
How the output data line is tri-stated.
Somehow this is one way of doing that, you can do it in some other way also, that when the chip is not selected or neither read nor write is active, we want the output data lines to be tri-stated. This is just one way of doing it, you can do it some other way also, this is not the only way. And if you have asynchronous read write now, then you can make some small change to the design. This is the same memory module, but with asynchronous read and write. So, you observe the difference. Now, in the parameter you have no clock, only read write chip select. This assign is as usual the same. This always blocks, the body of the block is the same, but the triggering condition is different. Now, here you execute this if either the address changes or the data changes or there is some change in read, write or CS. See, this is what happens in a typical memory chip you use. If you change the address, immediately the data out changes, that is the behavior. Okay. So, here you can model it like this. Similarly, for read, if any of the signal changes, you do the needful. Maybe if any of the signal changes, it is not really a write, then this condition will not evaluate to true, anyway write will not take place, but you will be checking it whenever there is some change in one of the inputs, right. Fine. So, these are for RAM chips, RAM systems, but if you have a ROM or a EEPROM where you only want to read something, the data storage is permanent, then you often model it like this. So, here you have a ROM where you have address data, you have a read enable and a chip select. Of course, read enable is optional, but here I assume that we have both read enable and chip select, both has to be activated in order to read the data. So, just for the sake of illustration, I have assumed a very small memory module which consists of 8 locations. The addresses ranging from 0 up to 7. So, number of address lines will be 3, read enable and CS will be inputs and output are 8 bits, this each word is of 8 bits, this we are defining as a register type. And in an always block, we say that whenever address or read enable or chip select changes or not changes, yeah, wherever address, I think, see, inside the block there is a case statement where depending on the address I am applying, I am saying that address 0 contains 22, 1 contains 45, 7 contains 12 and so on. So, these will be the data that will be stored. Actually, I have written this incompletely. So, actually you will have to write data equal to 20, not simply 22. This will be data equal to 22. This will be data equal to 45 and data equal to 12. Yes. Yes, yes, yes. So, this condition is also not correct, I believe. This will say if either the address changes or both these two are active. So, read enable and CS, something like this, then only you read the data. Okay. Fine. Right. So, we have seen that means how we can model memory for our you can say basically modeling purposes. For most small designs we can model memory like this. As I said again, means I am repeating, if your purpose is to simulate, for simulation you can use this way of memory modeling. So, at least up to the behavioral design verification through simulation you can use this model, but after that while synthesis you can instantiate the blocks from the library and you can start doing it from there. But now one thing which we have been talking about, so after you have written the program, you want to check it through simulation, you need to write a so called test bench. So, now let us see what is a test bench really and how it is written. See, a Verilog test bench is essentially a Verilog program. Make this point, it is a Verilog program. It is a procedural block like the always statement, but the difference is that an always procedural block executes indefinitely, it executes in an infinite loop, but a procedural block that is used in a test bench is executed only once. This is the main difference. Initial block. So, I had said earlier that there are two kinds of procedural blocks. One is always, which we use normally for design modeling, and the other is called initial. Now it is the property of this initial block that it is executed only once, and this is what we need when you are trying to run the test bench, because whatever we have written in the test bench file, that has to be executed only once, not repeatedly every time. Okay. Test bench is obviously used for simulation, you are not using it for synthesis. Test bench is something which is simply used to check whether another design you have made is correct or not. So, a test bench can contain some constructs which cannot be synthesized, like you can have a statement read from file, you can output something on the screen, you can specify explicit delays using hash, those things you can do in a test bench, right. And also the test bench will be generating whatever signal is required to test the other circuit. Well, other than the test vectors, it can have clock, it can have reset, and enhancements, any other control signals you need, right. So, we will see at some examples, look at some examples to find out. So, broadly speaking, this picture summarizes what is a test bench. See, you have a module under test, this is a Verilog program. You have the test bench, this is also a Verilog program. Verilog program will be applying some stimulus to this module, and the module under test, whatever output is coming, it will be checked by the test bench. Now, you see, module under test is also a Verilog program, test bench is again a Verilog program. Now, whenever you are using a test bench for verifying the design of this module, what actually you are doing is that you have your module under test, you have your Testbench. These are two independent Verilog modules. Now you wrap both of them into a top level module. Now in the top level module, you use this MUT and TB as if they are already pre-designed blocks. You simply instantiate them and you interconnect them as required, as that's shown in the earlier diagram, previous diagram, that the MUT and the TB needs to be interconnected in this way. So you also specify how they are interconnected. You simply instantiate these two blocks, specify the interconnection, that is all. Now let the modules execute and they will do whatever is to be done. I will give an example of how it is done. Fine. So now let us look at ways of writing the test bench. Of course, we will not be talking about all the features available, we will be looking at some of the more popular features. Okay. Now let us look at some of the general rules for writing the test benches. First rule to be followed is that you start by creating something called a dummy template. Dummy template, what it means is that, say you have your module under test, say this is your MUT. MUT will be having some inputs, this will be having some outputs. Now in this dummy template, all the inputs which are coming to the MUT, you declare them as reg type variables, and the outputs, that you declare them as wire type variables, right. Second, you instantiate the MUT as I had just shown in the previous diagram. You have to instantiate the MUT as well as the TB. So you instantiate the MUT. And second is that before you start the actual testing process, you may need to initialize some of the values in the MUT. For example, if your design is just a simple counter, then you may need to reset or clear the counter to start it to the known state, say all 0. So the next step will be, you will have to initialize. Now in the initialization, you will have to assign some known values to some of the MUT inputs. Depending on what kind of MUT you are designing, there can be some reset signal, some clear signal, so on. And if your MUT has a clock, you will also have to specify what is the frequency of the clock, what is the duty cycle, all these things you have to specify. There are ways of doing it, we will see how. So clock generation logic. These are essential, and in addition you can include several simulator directives. We will be just explaining this. There are in fact many others, I am only explaining some of the more popular ones. See, all the simulator directives start with the $sign. They are the special keyword kind of things which has special meaning to the simulator. Display, monitor, dump file, dump variables, dump vats, and finish. So let us see what these mean. Display is just like a print statement. So whatever you give as an argument to display will be printed on the standard output, which is the screen. So it is like whenever you want to output a string or a message at some point in your test bench file, you give a display command. So that whatever you are giving, that will get displayed. The syntax is similar to printf in C. So the syntax is same. There is an alternate form of display that is called monitor. Monitor is also doing the same thing. This is also printing the specified string or the variables whatever you specify in the parameter, but there is one difference. Monitor is something like a trigger. Trigger means it remembers that, well, this is the thing which I have to print, but it will not print immediately. So every time any one or more of the variables in the parameter changes value, it will print automatically. So it is not a sequential statement like print, like that display. display will be executed when it is encountered in sequence of code, but monitor is a code. It is like say for example, you are installing an interrupt service routine, something like that, that you are installing an interrupt service routine, but the routine will not be executed now. The routine will be executed every time a variable changes. So, every time you see a change in the variable, that monitor command will be printing whatever there is there in the parameter list to a file or to the screen, wherever. So, that will give you the result of the simulation. You can exactly see that at what times the values are changing. Okay. So, using the monitor command you can do this. It prints the value whenever the value of some variables in the specified list changes. At the end of the simulation, you give a finish command which tells the simulation to terminate and close all the files which it had been using. Okay. Dump file and dump variables, these are two commands which are often used by the simulator in conjunction with an auxiliary tool which is called the signal viewer or signal display. Now, in the different simulators they are called by different names, but the idea is similar. See, the first command dump file, it simply specifies the name of a file, nothing else. In dump file you specify a name of the file where some information will be outputted, and dump vars will dump all the signals that are there in your specified module into that file whenever there is a change or after each instant of time. So, after simulation, if you look at this file which you have specified, you will see a long streams of zeros and ones which have been written into it with the times. At this time the value of the signal is 0 1 1 0, at this time the value is 0 0 1 1 something. Now you have another tool that I had mentioned, signal viewer. That tool will be reading the data from the file and will be pictorially displaying it on the screen in the form of timing diagrams. Okay. So, this is what I mean by saying here that this file is used for storing the waveform. So, actually you are not storing the physical waveform in the file, but the data for those.
So, this dump
Yes.
vars and monitor and all these will be only with respect to that particular module in which we give this, or with respect to
This will be only with respect to that particular module, that Testbench module that we are using on. Yes, not outside that. Scope of this will be only within that module, right. Okay. So, now let us look at some example test benches. Fine. So, in this example we are considering a shift register. Now, here we are only showing the test bench, we are showing only part of the thing, not the whole thing. Module, shifter, top level. Here we are instantiating the shift register module here. This description I am not showing, this have been defined elsewhere in another module. So, this is instantiated as a block S1 in this design, and the inputs are clock, clear, shift and data. So, clock is there, clear is there, shift is there, and data is the value which is coming out. These are the input and output signals. Data is 8 bits. Now, you see there is an initial statement here. Now, initial statement means that this is a test bench. Now, initially you see what we are doing here. First is that we are initializing something. This part, the first part of the initial block, this is initialization. Here we are initially setting the clock signal to 0, clear signal to 0 and also shift signal to 0. We are assuming all these are active high. These are the initial values we are setting. Then you just look at this statement. We are saying always after 10 units of time clock equal to not clock. This is one way of specifying the clock signal. This will say that the signal clock will be going high and low continuously, and these delays will be 10 units of time each. Right. So, this is one way of specifying, always #10 clock equal to not clock. This, so just let me write. Okay. So, always here there is no parameter here, as you see. So, it is triggered always, there is no triggering condition in parenthesis after the always block. So, it is an unconditional always block. So, say after #10 you say clock equal to not clock. So, this kind of a declaration you can use if your duty cycle is exactly 50%. The waveform is symmetrical, but if you want a different kind of waveform, for example, the on period is less than the off period. So, you have 2 here and you have 10 here, say, then you can specify it like this. Always you will have to give a begin here. After time instance 2 you make clock equal to 0, after time instance 10 make clock equal to 1, end. This is the way of specifying an asymmetrical clock. And if in some design you need to apply an arbitrary waveform, delays are all different, then you can write a sequence of such statements, after time 2 this, after time 10 this, after time 5 this, after time 8 this, so on. But since clock is a continuously generating, we give it in an always block which is executed indefinitely, and you can specify the duty cycle or symmetrical, whatever.
What is a typical clock?
See, typical clock in case of simulation, it really does not matter. Simulation, these numbers you specify, those are some time units you specify, that you can give some numerical values by giving the times, just using the time scale command I talked about earlier. Now, using the time scale command, you can say that your 1 unit of time is actually 1 nanosecond. But since you have not synthesized the design possibly, that 1 nanosecond does not mean anything. On the timing diagram, the unit will be 1 nanosecond, that is all.
What about the typical clock in general
Digital
digital circuits?
circuits, well, as you know, nowadays if you have a good design, you can run a circuit above 1 gigahertz. So, the clock frequency will be 1, the time period will be 1 nanosecond.
There is no terminating condition in this test bench.
This, as I said, that this is incomplete, just means I have shown a skeleton. I will show a more complete version.
Time scale is not specified. Time scale is specified only when we need it during the actual.
Time scale, if you do not specify, it will take as a generic unit, 1 unit of time. So, absolute whether nanosecond or picosecond or second, it is not specified.
Because anyway in synthesis it is.
Yes, during simulation you may be only interested in checking the functional behavior of the circuit. Delays and other characteristics will be checking later after you have done synthesis. Okay. Fine. So, now let us look at a more complete version, because the earlier version did not contain everything, only a few of the statements. So, in this version the first part is the same, this continues on the next page, I will show the next page. This first part is exactly the same as we had earlier, same shift register instantiated as S1. In this initial block, first there is a begin end, this is initialization and this is clock generation. Now, after this, see, there can be more than one initial blocks in the design. Now, here for example, this is one procedural block executed only once, this is one procedural block executing continuously. Then you can have as many such blocks as you need. For example, you have another initial block here executed once, you have another block here executed once, you have another block here executed once. So, you can have as many number of initial and always blocks in a program. If it is initial, it will be executed once, if it is always, it will be executed as many times specified, and these blocks are all concurrent. It is not that first this will be executed and then this. Okay. Now, let us see what these initial blocks are doing. The first initial block is specifying the name of the dump file where the data will be dumped for waveform display. Well, some simulator use the extension .vcd for this file. So, I have also shown it as .vcd, and this is followed by a command dump vats. Dump vats means whenever I give this command, then whenever some variable changes state, all the values of the variables will be automatically dumped to this file. But if you do not give this command, the dumping will not be automatic. Okay. And here in the next initial block, we start with a display. See, display is like printf, I told you.
So that
Yes.
dump value is not taking the file as an argument.
Dump vats will by default take the file name specified by the previous dump file command.
But if dump file is not there,
Dump file not there, this will give an error.
What is shifted there?
file.
Just a name of a file.
So dump file is for dumping the waveform. No?
Dumping the waveform. These two statements are only for waveform analysis.
Which signals will be dumped? All the signals.
All the signals that are defined, because in the waveform viewer you can specify which signal you want to see, which you won't. So, your file should contain information about all the signals. Okay. Now, in the next initial block, you are actually displaying the input output of everything on the screen of all the signals you want to see. The first display command is like a header, you are printing a header, time, CLK, CLR, SFT data. /t is a tab. Using tab, you properly want to display it in a tabular form. This is followed by monitor command. Display is executed immediately, so the header is displayed. Monitor, this is like a printf statement again. You see, there are 5 things you want to display: time, this is a system time, this is a simulation time, $time. Simulation time unit is advancing 1, 10, 20, whatever. Clock, reset, clear, sheep, data. See one thing, this $time does not require formatting stuff out here. So, you can see there are 5 other variables, there are only 5 out here. And of course, here I have not given tab, you should have given this tab here, so that it is displayed properly in a tabular way. Okay, so /t, %d, /t, %d, that should have been the right way of giving it. Anyway, so monitor says that whenever any one of these variables change state, you print it on the screen. So, on the screen you will be getting a nice printout of all the signals as they are changing. End. This is this block. And the last one says that you continue whatever is being specified up to 400 units of time. So, at 400 time units you finish. Okay. There can be some additional code which follow this also, like you are applying some specific input pattern to the module under test, checking the output, that also you can do here. So, you can edit as much as.
So will you please go to the previous slide?
Sure. The
Sir,
previous
how
slide.
are you integrating that shift register with this column module?
Okay, your question is how are you integrating this with the test bench. So, that I have not yet mentioned. Let me now look at a complete example that will show exactly how you will normally use it. So, the whatever I have shown till now is just for the sake of illustration. This is your main module, these are the functions you write as test bench, you integrate them. But normally, as I have shown an earlier example, that is how you normally do it, you usually do it. Like you have a module under test, you have a test bench, you instantiate both of them inside a top level module. That is how you normally do it. Now, means I will give an example of like that. Okay, in this example, this hash 400 finish means at time 400 the simulation should stop. So, whatever I have mentioned, clock, everything will stop as soon as time reaches 400.
But the initial blocks, they will be executed only once. No?
This is also executed only once. This is a delay.
Like whenever all this is executed first time, all these blocks are also executed.
Yes.
So
That's it for
when
initial.
always executed next time.
Hmm.
So what happens to these blocks?
These blocks are executed only once. For example, this hash 400 finish, this will make an entry to the simulation event queue, simulator event queue, that at time 400 there is an event that we have to process. And as the simulation time advances, that simulation queue is maintained as a priority queue. So, that whatever time is earliest, that event is processed earliest. So, at some point in time, this time 400 will be the first one. So, you will say that it is the finish event, you close everything and stop. The always will also be generating an event. Clock is changed every 10 time unit. So, clock will go up 10, 20, 30, 40, 50, 60, it will go on changing.
So this dump values keeps dumping whenever the changes take place in the value.
Yes, yes.
So now in the previous slide, I'm not clear with how the variables are integrated. Like the variables of S1 and the variables of this.
Yeah, I understand your question. I will show the next example. You will see that how it is integrated, because this example shows the complete picture. Okay. Here I am showing the total thing. There is a module under test, this we are calling XYZ. There is the corresponding test bench, this we are calling test XYZ, and we are integrating both of them like this as part of a top level module. Let us see how. Well, you see this module, the first one, here there are no parameters, because this is the top level model. Top level model is just like a black box, nothing goes in and nothing goes out. This simply encapsulates the module and the test bench, nothing else. So, there are no parameters, and in this example there are 3 interconnecting signals. We call them this is W1, W2 and W3. W1, W2, W3 are defined as wires. You instantiate one copy of XYZ out here, you instantiate one copy of the test bench out here. One you call them M1, other you call M2. So, when you will be seeing the modules and the test benches, you will see that they contain 3 parameters W1, W2, W3. They are specified in the same order. So, here you instantiate this, here you instantiate this. Now, the way or in the order you have specified the parameters, this will define the interconnection. Okay. Directions will be defined by which you have defined as input and output in the modules. Like in XYZ, you see here XYZ module, here F, A and B. A and B are defined as inputs and F is the output, and inside it, it is defined as a simple NOR gate which has a delay of 1 time unit. NOR gate takes the parameter, NOR is a primitive, I told you earlier. First one is the output, second and third are the inputs. So, you see for the test bench, the first one is the output, second and third are the inputs.
So that hash one with the NOR gate
Yes.
is specified before the NOR is.
That can specify anywhere, before or after, anywhere you can specify, because this is a predefined model. You are like you are instantiating, you can give it means this hash 1 you can either give before or after, it makes the same thing, same meaning.
Name should be there,
NOR then S and 1 and 2.
NOR that is optional, because names you also drop, because the signals which are specifying here, they will define the interconnection, and if you do not specify the names, by default U1, U2, U3, U4 some name will be assigned by the synthesizer when you synthesize it. Okay. Fine. All right. So, here we have defined the test bench, we have defined the XYZ module. Then let us see how we can define the test bench now. The test bench will look like this. Test bench will also be having the signals F, A and B, F, A and B, but now F will be the input, A and B will be the outputs. Why? Because in the XYZ module it was actually a NOR gate. So, here whatever you are calling as A and B and whatever you are calling as F, in this test bench this A and B has to be fed out, okay, into it. So, for the TB these are output signals and this has to be fed in. For TB this is the input signal. So, now you look at this. So, this AB is our output, that is why they are defined as reg. There is an initial block, this is a pure combination circuit, so no problem, no clock. Monitor you show like this, you display the time, $time you can give anywhere, either just before or after the string. You display the time, then you display A equal to, B means binary, B equal to, F equal to, ABF. This ABF are single bit variables, they will display the A equal to 0, B equal to 0, F equal to 1, something like that. Now, here you are applying the test vectors. This is one way I have mentioned. You specify the delays, after 10 time units of time you apply A0, B0. So, after 10 units of time again you apply A1, B0, after 10 A1, B1, after 10 finish. So, this is just a very simple example I have illustrated, but this illustrates everything.
So that after 10 is taken parallelly or
Sequentially.
10 units after the first.
Sir, like in this example, only XYZ is the synthesizable block.
Only XYZ is a synthesizable block, test XYZ is not.
Sir, so actually, what is the need of the top level module? Like we can run both of these programs, the test bench and the module.
See, now the question is that what is the need of the top level module? So, need of the top level module is nothing but flexibility, because I am telling you right now the example I have shown, you have a copy of the XYZ, you have the test bench. Now, you can have another scenario which can happen after you have done the synthesis, like you can have a scenario like this, you have this XYZ, okay, this you have written as there, you give this specification to the synthesizer, you carry out synthesis, okay, you get another version of XYZ, this we called XYZ S, and you already have test XYZ, but of course you will have to modify test XYZ now. Now what you do, you integrate these three in the top level module. Now, as part of your test bench you can do that, you apply this vector here and here, after that you compare the outputs whether they are equal or not equal. If they are unequal, you flag some error message, that also you can write as part of the test bench. But just putting them together at the top level module is just for convenience and modularity, nothing else.
And then module X5 where
Yes.
you are given one delay #1 before NOR.
Huh.
That is not synthesizable.
This is not synthesizable because synthesis tool will be ignoring this. Yes, you are true. Yes.
So do we say in the last slide?
Yes.
So do we really need to give the parameters F, A, and B in the test bench?
Here F and B.
Yes, sir.
Yes, we need to.
But how is it helping?
No, it is a Verilog module, and these are the input output parameters. That's all.
Basically, you can instantiate if you can declare them as wire and register A and B, sir, then the output will be the same.
Yes.
How is it helping them?
No. What I am saying is that whenever you are doing this kind of instantiation, these are defined as individual Verilog modules, and whenever you define a Verilog module, just like a function you write in C, you have to specify all the signals coming in and coming out. That has to be there as part of the parameters. This is mandatory. But the top level module, in contrast, it does not take anything in or anything out. That does not need any parameters.
See what he is saying, like he is saying in the test bench only, you instantiate the design module. You can do that.
That is what I had shown in the earlier example.
Earlier example was like that.
That is what I showed in the earlier example,
But he
because
says how is it helping?
To create another.
no, it is simply helping in case of modularity. Say,
Visualization of the problem.
yeah. because you can have several versions of the test bench also. One is a simpler test bench, other is a more exhaustive test bench. You can just include the one you need and you can relearn it. Okay, so from the next class onwards we will be starting our discussion on synthesis. That is how we